what we're going to do is start down the path of creating a virtual machine, which is just a fancy way of saying what we want to do is to make sure that we can take the hardware that we have, you know, the disk and the network interface and the video monitor and the CPU, of course, and share it amongst a bunch of different running programs, hopefully with a fairly low overhead. So we're able to switch from program to program to program. We'll be able to timeshare the machine amongst a lot of different programs that are all running simultaneously. And each of the programs will have the illusion of having a complete machine to itself, and that's the virtual machine. So what we're working on today is technology to sort of timeshare one physical piece of hardware and create the illusion of many virtual pieces of hardware, many virtual machines. And our first step in that direction, which we got started on last time, was virtual memories. So what we have is we have the CPU that's producing a virtual address, and we treat that virtual address. So here's the 32-bit address coming out of the CPU. So we have the virtual address. So that's the address that's produced by, you know, that you think of when your program is running and producing addresses. That's the address that we're talking about. And what we want to do is we're going to treat this as sort of a two-component address. There'll be a page offset, which is some number of low-order bits, and then a higher number, so we have and then a virtual page number. So we're sort of splitting the address space into a bunch of pages. You can think of those as contiguous little sections of the address space. Typically, they're you know, maybe, you know, 2 to the 12th bytes, you know, 2 to the 16th byte, something like that. So some 12 or 16 of the bottom address bits are used to indicate where we are on a particular page, and the rest of the 32, so altogether we have 32 address bits on the beta, and the rest of the address bits we treat as the page number. And what the MMU does is that it translates a virtual page number into a physical page number. It's just a very simple table lookup that allows us to take a particular range of virtual addresses and turn them into the same size range of physical addresses, but not necessarily located. So here we have virtual page 0 sort of looking like it's mapping to physical page 0, but there's really no reason why the physical page has to have the same number as the virtual page. So the idea is that the MMU, its job is to come up with a physical address which has the same page offset, but in its high order bits has the physical page number. So the MMU does that mapping. Yes?
A page is just a group of consecutive memory.
Right, so you know, in some ways you can imagine we could map each physical address to each virtual address to a physical address, but you know, we'd have to have 2 to the 32 separate translations, 4 billion separate translations, which is far too many really to implement. So what we choose to do is instead do the translations page by page. So a page is really just a collection, as I say, of 4096 or 8192 or some power of 2 number of bytes that we're going to treat sort of as a chunk. And we'll move that chunk from disk into main memory and then back and forth that way. So all of our memory management is going to be at the page level for this sort of discussion. And we have these 2 extra control bits in the table. One is resident, that tells us whether or not that virtual page is actually present in the physical memory. And the other is the dirty bit that keeps track of whether, when it comes time to throw that physical page out of memory, if we want to throw that virtual page out of memory, whether or not it's been changed, it has to be written back onto disk, changed by a store instruction. So our translation mechanism really is a 3-step process. The first stage, what we're going to do in order to get reasonably high speed, is to take the virtual page number and look it up in a small cache, a so-called translation look-aside buffer, and to see if we have the VPN to PPN translation cached. Because the tables that we're talking about get pretty large, and we don't want to put them all in fast RAM. So instead we use a very fast little memory. So this typically happens quite quickly, and it's like a fully associative cache. It can be, you know, 16 entry or 64 entry fully associative cache, and it will have very, very high hit rates, because once we start dealing with a particular set of virtual pages, we're likely for many, many accesses in a row to access the same virtual page. And if we have the physical page number, then we can quickly come up with the information we need to complete the address. So we combine the physical page number with a page offset. We know exactly where to look in main memory, or in fact, typically in the cache first, the actual memory cache first. And then if we miss in that, we go off to main memory. If we don't have the information we need in the translation look-aside buffer, we have the slightly more time-consuming process of using the virtual page number as an offset into a table that's typically stored in actual main memory. And we can fetch the information from there, but that would be an actual memory access that we have to make. That information can be used to complete the translation process to come up with the actual address. And at that point, we often cache the physical page number information back in the TOB, so that once you've accessed a virtual page and have to go through the translation through the page table, once that translation is complete, we'll put it in the TOB so that subsequent accesses to that virtual page go much more quickly. Okay, and then finally, if the page is not resident, if the R bit is off, then what we need to do is to go off and as we described last time, deal with this problem of not having the page physically resident in memory. So now we'll read it in from disk.